In this video, we present a method for vectorizing line drawings, and in particular single line art, with the correct parameterization along the curve. From Picasso to modern artists such as differently, single line drawings have been used as an expressive form of art. Single line drawings are a very demanding type of line art, where a single continuous curve represents a whole object or scene. They require great abstraction skills from the artist to capture the essence of what is being depicted. These drawings are often created in a raster format and must be vectorized to get an easily editable digital version. For single line drawings vectorization, one of the main difficulties comes from the intersections, since it is not always easy for an algorithm to find the correct connectivity of the curve. For instance, this intersection can be drawn in 3 different ways. The 2 strokes can cross each other like this, or they can touch in 2 ways like this, or like that. State-of-the-art methods often produce multiple strokes and do not properly handle intersections. For instance, Adobe Illustrator produces this result, which contains multiple strokes with intersections not correctly connected. This is visible here, there, and here. More recent state-of-the-art research methods, like the one proposed by Yin and colleagues, produce better results. For instance, this intersection is correctly handled. However, this one is not. And this one neither. Our method produces a realistic parameterization, which can be visualized through the drawing order of the line, or through a color gradient. All intersections, such as this one, that one, or this one, are correctly handled. We now describe how our method works in detail. The input is a raster image of a single line drawing. We first binarize this image using a simple threshold, determined using Lee's method. This binary image is then vectorized using potrace. We obtain a shape, outlined by Bezier curves. We then sample points on the contour of this shape and extract the medial axis through the Voronoi diagram method. This medial axis is pruned using Rohn and Jou's method. The medial axis faithfully represents the center line of the simpler parts of the drawings, but it doesn't capture intersections correctly. For instance, there should be 2 degree 4 nodes here. We thus simplify the medial axis by merging pairs of degree 3 nodes. To find which nodes to merge, we do not rely on the Euclidean or geodesic distance, as these can be misleading. Instead, for each branch of the graph, we compute the minimum distance from the medial axis to the shape outlined, meaning the width of the narrowest spot on the branch. We repeat this process for all branches. For each degree 3 node, we only keep track of the branch that has the largest value of the narrowest width, and we merge the degree 3 node with the other degree 3 node on that branch. Once the medial axis has been simplified, we detect the endpoints through simple heuristics. We then extract a crop of the input image around each of the degree 4 nodes. These nodes are intersections that can be crossed in multiple ways. We use a small convolutional neural network to classify each intersection between crossing and tangent. The network is trained on a synthetic dataset we created for this purpose. Using this information, we traverse the medial axis graph starting from one of the endpoints. Note that at degree 3 nodes, we use tangent continuity to find the direction in which to proceed. Finally, once the nodes are correctly ordered, we fit a parametric curve to the graph, which can be easily converted to a series of Bezier curves. In addition to our automatic method, we created a graphical user interface, allowing easy interaction with the results of our algorithm. The software is attached to the submission. The user inputs a drawing that is automatically binarized. Then one can compute the simplified medial axis, vectorize the drawing, and then export it. At any step, the user can modify the output of the algorithm. The threshold can be adjusted to account for thin lines. If the graph is incorrectly simplified due to insufficient resolution, one can split and merge nodes. Note that in most cases this kind of error can be solved with an increased input image resolution. If an intersection is ambiguous and has not been classified in the desired way, one can quickly flip its type. Thank you for your attention.